Hello, so in this video we're going to be looking at this idea of this thing called separable equations. Okay, and the idea is perfectly simple. So say like if we have a first order linear ODE, okay, so we have, remember what first order and linear means? First order means that the highest derivative in our equation is the first derivative. Okay, and it's linear, which basically means that our function or our derivatives aren't raised to any power. Okay, we've just got the function or the derivatives. Okay, and that's generally what we look at in this course. Okay, so let's suppose that we have something. We'll have say like dy by dx. Okay, and that's say like equal to something on the right hand side, which will have say like x's or y's in. Okay, so we're just going to say it's going to have x's or y's, and so another way of writing that is just saying it's a function of x or y. Okay, so an example, say for example, we could have dy by dx equals 7y plus x squared. That's perfectly fine. Okay, the left hand side, the highest derivative in this equation is the first derivative, so it's a first order. That's fine. Tick that box. And it's also linear because the functional derivatives aren't raised to any power higher than 1. Okay, it also works as well if the right hand side is not linear. Okay, so this is with constant coefficients, right? So this is with constant coefficients. You've got a constant coefficient there. Okay, but what I'm basically saying now is, let's say for example, if the right hand side, something like this method also works if the right hand side, say like doesn't have a constant coefficient. So say like if it's I don't know, cos x y plus x squared. Okay, something like that. That will also be fine. So in other words, it works for constant coefficients and also for variable coefficients as well. This method works. Okay, and the idea is that basically we can rewrite these things such that we end up with the right hand side being 0. Okay, so we'll end up with, how can we rewrite this thing? Well, it can be, the idea is that we can, well, I'll show you how we can, the general form that we can rewrite it. Basically, we rewrite it with a function m, and that function could be on xy, it doesn't matter which. Okay, xy, and then it'll be plus n, another function, xy, and this one is times by dy by dx. So that the n is, if you like, the coefficient with an nx. Okay, with a dy by dx, and that's equal to 0. So in other words, we can, and you can rearrange any first order linear differential equation in this way. In this way, that's absolutely fine. So for example, let's just rearrange this one in that form. Well, let's first of all just take it over to the other side. So 7y plus x squared. Okay, plus dy, sorry, that's, what would that be? Oh, sorry, I forgot the minus then, didn't I? I forgot the minus, so there should be a minus in front of that thing, plus dy by dx, yeah? Just taking that over to the left-hand side, and that's equal to 0. Well, that's in that form, that's in this form, right? Because this here now, this minus 7y plus x squared, that's my m, okay? And then if you like, there's a 1 hiding there, okay? So my function there is just n. Okay, then my function multiplied by d, which is multiplying dy by dx, is just my n, right? So therefore, in this case, m is minus 7y plus x squared, and my n is just 1. Okay, let's do the same with this one. So we end up with minus cos x times y, yeah, plus x squared. That's a minus a whole of that, plus dy by dx equals 0. Okay, well again, my m is that thing, and my n is just 1 again. Okay, so basically the idea is that you can rewrite any first order linear ODE in this general form with some function plus another function times by dy by dx, and that's all equal to 0. Okay, and we can actually write this in what's known as differential form. So in other words, the differential form, if I just show you, it's a differential form now. Differential form. And the whole idea of differential form is that basically we don't have dy by dx. We rewrite it in such a way. It's, again, we just consider this dy by dx a fraction, essentially. Okay, and we can just rewrite this dy by dx. So it's effectively differential form doesn't have this dy by dx. So what I'm saying is that we just multiply through by this denominator, just like with when we're solving any equation, if it's not differential equation, just with any kind of normal real equation, in order to get rid of fraction, we basically multiply through by whatever's on the denominator. We don't normally like dealing with fractions in equations, right? We always like dealing with whole numbers. It just makes things easier to work with. So likewise, we just multiply through by dx, and we end up with differential forms. So let me just show you what we mean. So we have m of xy, I'll just write out what we had up here again, plus n of xy dy by dx. So I'm writing out exactly the same thing as we had above, but now what I'm just going to do is just multiply through by dx. Okay, so obviously 0 multiplied by dx is still going to be 0, okay, and so then this is what's known as differential form, okay, and the idea is then that we can then somehow solve that just by integrating both sides, so the integral of that side and the integral of that side. Well, the integral of this side, okay, fairly obviously the integral of all that, we can just split this up into two integrals, okay, split this up into two integrals, so that's what I'm meaning, and then that's fine, okay, so this is kind of what we're after, and we call this then separable, separable, yeah, because obviously we can basically, you know, whatever we started with, say if we started with that, we can separate it into something that looks like that, or whatever we start with, okay, so the best way to kind of see, that's the idea, the best way to kind of see it is with an example. So let's start with dy by dx equals x squared plus 1 over y squared minus 1, okay, and so what we basically need to do is need to first of all take the first of all what we basically need to do is take everything in, we need to, yeah, I'm mumbling now, aren't I? So basically we need to get rid of that thing on the bottom, so just multiply through by y squared minus 1 effectively. Dy by dx, okay, is equal to x squared plus 1, okay, get rid of that dx just by multiplying through by dx, okay, that is my well, let's look at our general form. Thing with the dy is the n, yeah, so that now is my n, my y squared plus 1 is my n, and the thing with the dx is my m, so that thing now is my m, okay, so that's m, that's n. I can now integrate both sides quite happily, so let's just integrate both sides just for completeness. Let's do that, okay. So what's the integral of this? This is going to be a third y cubed minus y. I'm not going to worry about the constant with the dy for the moment. I'll stick it over with the dx. Okay, just like we did before with separation of variables. I'm just going to stick it with the dx. So I'm going to end up with third x cubed plus x, and then I'm going to have plus some constant hanging around at the end. Okay, so that's kind of the idea of this. Now, quick mention about explicit and implicit. At the moment, this is what's known as implicit. Implicit. The reason why is because it's not given as y equals something involving x. Okay, so something involving x on the right hand side. Okay, as you can see here, I've got third y cubed minus y. So if you like, you know, my y is defined in terms of a function itself. So y is defined in terms of function. My x is also defined in terms of a function. So in other words, what I've got instead with explicit is that I've got my y defined as a function, and that's equal to my x defined as a function as well. Okay, whereas with explicit, it would be, that's badly written, but explicit would just be y is equal to some function in x. All right, so I'm not even going to bother trying to rearrange this. I'm just going to, you know, that's all you need to know. This is at the moment is implicit because this is a function. This is a function here. Okay, now that's fine. That's fine. But the idea is behind kind of where we need to go next is whether it's exact or non-exact. Okay, so I'm going to quickly talk about this, but we're going to talk about it in more detail in the next video, if that makes sense. So it's a good introduction now. Okay, so non-exact and non-exact. So basically, you know, we could rearrange our first order linear ODE like this. Okay, so this would be dx plus n of xy times dy equals 0. So basically, we can rearrange it like this in differential form. Okay, and the idea is that basically we have to say, well, let's suppose that there exists some function, let's call it phi, and it will be dependent on variables. There exists some function such that the derivative of this function with respect to x is going to be equal to m. So in other words, you know, you can see there that m dx, you know, when we integrate it. So the dx, if you like, the dx is with the m. Okay, so we say that basically there exists some function phi that when we differentiate it with respect to x, we end up with m, okay, and that there exists some function, same function when differentiated with respect to y, is equal to n. Okay, basically where that comes from. Maybe if I, stop skipping steps and just kind of show you where that comes from. Essentially what we say, if I just get rid of that for the moment, we'll get there. Okay, what I basically say is I suggest, right, there's one function that is equal to, so this function here, that is, suppose there exists some function, if you like, it's the solution to this equation, right? There exists some function, and we're going to call it phi, such that that's equal to the first part here. So the integral of m of x, y, dx. So the phi satisfies that first function, and also phi satisfies that second function as well. So in other words, phi also satisfies the integral of n of x, y, dy. Okay, so basically it satisfies both functions. So therefore that implies that the derivative, if this is the integral of m with respect to x, then the derivative with respect to x must be equal to m. You happy? I've just gone from there to there, just by using the fact that integral is the opposite derivative. Okay, and same kind of thing, that implies that derivative of phi with respect to y is equal to n. Yeah, so it's the same kind of thing going on. So basically, when we stick integrals, get rid of that. Where's that gone? There we go. When I stick integrals in front of both these things, I'm basically saying that phi satisfies that thing. Some function exists that satisfies both of these things. Okay, and so basically this is the kind of idea which we need. All right, so okay, so now if I plug this back into my original equation, where is it? Come on, there we go. If I now plug this back into here, if I get rid of all my annotations and such like, and I'm actually going to plug it into this form. Okay, so this is what I'm going to plug my phi function back into, because I know that m now is my special function. I don't know what that function is. Okay, phi is d phi by dx, so m is d phi by dx, and n I know is d phi by dy. Okay, so now if I just plug that straight back in, so I have, what did I have? I had m plus n dy by dx equals 0. So now if I just replace it with this thing which I've just found up here, so m is d phi by dx, okay, plus n, which was d phi by dy. Notice my use of partial derivatives as well. I should have stated it up here, but that's purely because phi, I know phi is going to be a function of both x and y. So phi is going to be a function of both x and y. So basically when I take the derivative, I have to choose which derivative I'm taking it respect to. It's a partial derivative, not an ordinary derivative. Okay, and I've still got dy by dx here equals 0. Okay, so therefore I can just do a little bit of cancellation here. The dy's kind of cancelled. Again, just treating it as a fraction. Strictly speaking, it's a chain rule. So I end up with del phi by del x equals d phi, plus d phi by dx. Okay, I'm just kind of skipping between ordinary and partial now, just because if I'm taking the partial derivative of phi with respect to an ordinary derivative of x, I can't do that. I have to take the partial derivative. Okay, if it's partial to start off with, it has to be partial right the way through. Okay, so the fact that this is an ordinary derivative here doesn't make a blind bit of difference. I have to change it to a partial. Okay, equals 0. So therefore that implies that 2 del phi by dx equals 0. Okay, which then implies that, what does that imply? That del phi by dx, if I just divide through by 2, I still equals 0. So therefore when I integrate this thing, that means that phi must be equal to some constant. Because if you think, if I'm saying that the derivative of some function is 0, so in other words, if I'm saying like derivative of some function is 0, then that means that the original thing must have been a constant. Because if you think about it, if you think about it, what's, say like, what am I doing? So y equals, say, 4, okay? Well, what's the derivative of y with respect to x? Well, that's equal to 0, right? Because I'm just differentiating that, and it goes to 0. So basically, if I'm saying the derivative is 0, then I'm saying that my original thing must have been some constant, right? So that's how I get there. And I can do a similar kind of argument with the case for, the opposite case, for d phi, I can do an opposite kind of case. Instead of considering this thing here, I consider it as m times, well, if I've got plus n dy by dx equals 0. If I multiply through by dx, I end up with dx here, right? Okay, then if I divide through by dy, I end up with dy here, right? And get rid of that dy there. So effectively, I can do exactly the same thing just by plugging in d phi by dx here. So I'll just quickly do it. Actually, I'm going to pause the video, go through it, and then I'll talk you. So all I'm just basically showing you now, just done all the working. All I'm just showing you now is that I can do exactly the same argument, but this time with, you know, with the dx dy instead of dy by dx over here. And you get exactly the same thing, exactly the same result coming out. So, you know, just replacing m with my d phi by dx and n with my d phi by dy. Okay, going through, and I end up with phi as a constant. And we basically say, it's exactly the same argument with d, you know, for dy as it is for dx, okay? Basically, if this is the case, then we say that our ODE, if, you know, we end up with our function being a constant, if we end up with this case, then we basically say that it is exact, okay? And exact cases are nice, because we don't have to pretty much do anything with it. It's basically exactly the same standard method that we kind of do. But if it's not exact, then that's not very nice. So I'm just going to finish off this video very, very quickly with kind of an important example, kind of tying all these ideas all together. Normally, I wouldn't rely on an example to kind of teach you something, but I think in this case, showing how it's done, you can talk generally to your heart's content, but I think actually seeing how it's done is really, really useful. Okay, so basically what I'm going to do first of all, by the way, another way of writing that it's exact is that if you look, we had, well, another way of showing it's exact is basically if we get a constant. So in other words, if dm by dy is equal to the derivative of n with respect to x. So basically, I always think it's the opposite derivatives. Okay, so if you think we had m dx plus n dy equals 0. Okay, so effectively we look here, and basically if that thing, but this time differentiated with respect to the opposite which we had here, and this thing which is the opposite that we had here, okay, it's just by the same reasoning that we had here, that basically needs to be a constant. So if we differentiate it with respect to the opposite variable, fairly obviously it should be a constant. Yeah, it makes sense that it should be a constant, because if you had y equals, I don't know, y equals 4x, okay, and if you differentiate or plus t, say, and if you differentiate that with respect to t, then, you know, it should be a constant. Go through and convince yourself. Actually, I'm not going to kind of waste your time going through there. Go through and convince yourself. But basically, we end up with this thing, and if that's the case, then it should be a constant. Right, so basically if the derivative of m with respect to y is equal to the derivative of n with respect to x. So first of all, this is just to check the exactness. Okay, so let's start with the example. So we have 2x plus y squared plus 2xy times dy by dx equals 0. So what's m and what's n? That's the first job. Well, that's m and that's n. So that's m, that's n. Put brackets around there, because that's in exactly the same form as kind of we had, or as we had here. So we have m plus n dy by dx equals 0. So we've identified m, we've identified n. That's the hardest bit over and done with. Next is just kind of following the method. So first of all, we need to check the exactness, and we check the exactness by checking this thing. So let's differentiate m with respect to y. Okay, so what is 2x plus y squared with differentiate with respect to y? Well, anything that's not y is just a constant, so that includes x. Okay, so the 2x is just going to be a constant, 2x is just going to be a constant, so that's going to go to 0, and this thing is going to become 2y. Okay, so that's 2y. Okay, now let's check this n. So let's check dn by dx. Okay, because that thing should be equal to that if it's going to be exact. So what's the derivative of this thing? Well, this time we differentiate with respect to x. So anything that's not x is a constant. That includes y. So therefore, effectively, it's just 2y times x. So what's x differentiated? Well, it's going to be 1, so it's just going to end up with 2y. They are equal, so therefore they're exact, so that's a happy case. Okay, we're happy with that. It's an exact case. Okay, now we need to find this phi. So we suppose that phi exists such that the derivative of phi with respect to x is going to be m, and the derivative of phi with respect to y is going to be n. Okay, so let's differentiate m. So what was m, remember? Maybe if I just write m down here. So m is equal to 2x plus y squared, and n was equal to 2xy. Okay, so this implies that if we just consider this case, we end up with phi is equal to the integral of m with respect to x. Okay, so basically the integral of m with respect to x is going to be the integral of 2x plus y squared with respect to x. Okay, so again, anything that is, we're integrating with respect to x, so anything which isn't x can just be treated as a constant. Okay, so that includes y. So the derivative of this thing is going to become x squared, right? So 2x is going to be integrated to x squared. Okay, and then the derivative of y squared, well, y squared is just going to be a constant, so we end up with y squared times x. So xy squared I'm going to write. Okay, xy squared plus some constant, and that constant is going to be dependent on y. And the reason why it's going to be dependent on y is because it's always going to be the opposite of what we end up there. Because if it was dependent on x, then, you know, we would have it included in this integral. So it would have to be differentiated, it would have to be dependent on y, because when we differentiate with respect to x, it should disappear. Yeah? If we differentiate with respect to x, it should disappear. If it was dependent on, if that constant was dependent on x, then when we differentiate with respect to x, it should be included in this kind of integral integrand here. Yeah, the integrand is the thing which we're integrating. So this integrand here, but the fact it's not included in this integrand here, therefore it has to be dependent on y, because when we differentiate with respect to x, it will just disappear. Okay, so it's kind of a stronger case of just a constant. Well, the question is now, what is that constant there? Well, to find that out, we need to now consider the case when we need to consider this case over here. So the derivative of phi with respect to y is equal to n. Okay, so so we know that d phi by dy is equal to n, which is 2xy. Okay, so but we also know we've now got an expression for y here. This is an expression for y. So therefore, if we differentiate this thing, with respect to y, that should also be equal to 2y. Okay, so in other words, this should be equal to, so if we differentiate this thing with respect to y, that's a constant, that's just going to disappear, so it's going to go 0. That's going to become, well, x is going to become a constant, but we've got 2xy squared there, so it became plus 2xy, yeah, plus 2xy, and then we've still got the constant dependent on y, so plus c dash times y. Yeah, that's the derivative of this constant with respect to y. Okay, so now I can just look at this, so therefore we've got c dash y plus 2xy is equal to 2xy. Okay, so therefore that implies that c dash y is equal to, if we just take the 2xy onto this side, we'll just end up with 0. So therefore our c dash y, so when we integrate c, it should just be a constant. So what this basically means is that when we differentiate c, okay, so therefore c is just going to be equal to 0. Okay, c is just going to be equal to 0. The reason why is because, well, we're saying that c dash is going to be dependent on y. Well, this side isn't dependent on y, clearly. Okay, so in other words, what we're basically saying is that we're considering some function, which is c of y, that basically when we differentiate it, it goes to 0. Well, the only way that can happen is if it's 0, because we're saying it's dependent on y. Yeah, so when we differentiate it with respect to y, then if it goes to 0, then there was nothing there to start off with. Because if there was something there, then you know, we could find out what that thing was. It would be non-zero on the right hand side effectively. So basically we can just say that c of y is equal to 0. So therefore our final equation, so phi is equal to, what was phi? It was this thing here. We now know that c is 0, so therefore we just know that phi is equal to x squared plus xy squared. Okay, so you know, that's a nice simple thing. Go through it in your own time. You know, it's really quite straightforward. Okay. The next case that we're going to consider though is when it's not exact. The exact equations are the happy equations. If it's not exact, then we're going to have to be slightly clever, and I'm going to take you through the thinking behind that.